If the sample is not infinitely thin, then some of the gamma rays produced in the sample will be attenuated prior to being emitted from the surface of the sample. How much they are attenuated depends on the energy of the gamma ray, as well as the composition of the sample and its container. We can calculate this attenuation if we know the geometry and the composition of the sample material. For uranium, we find that even small samples are still infinitely thick. This table shows the mean free path, or average distance a photon goes before absorption, of the 186 keV line, and the infinite thickness for this 186 keV gamma for various uranium compositions. The mean free path is calculated by taking the inverse of the product of the density and the mass attenuation coefficient, like so. Graphs of the mass attenuation coefficients are shown here, and the second graph gives the mass attenuation coefficients for gamma energies of interest for those of us monitoring special nuclear materials as a function of shielding material. Sometimes we're not after the amount, but we are very eager to know the isotopic concentrations of uranium or plutonium. Here is a spectrum of highly enriched uranium, and what's significant in this spectrum is what's not there. There are no signature emissions from uranium-238. The second spectrum is from low-enriched uranium, and you can plainly see the contributions at 766.4 keV and 1001 keV from the uranium-238. The next series of spectra here gives examples of uranium enrichments from 93% enriched to depleted uranium at 0.2%. Note the progression of the spectra as the isotopic composition moves from U-235 dominated to U-238 dominated at 0.2% U-235. The uranium-235 line at 186 is almost gone. We can do the same thing with plutonium. Plutonium isotopic concentrations are, again, relatively straightforward to measure. Low burnup plutonium has a relatively small amount of plutonium-241 signal compared to reactor grade or high burnup plutonium.